So let's go and have a look at investment timing. So the basic question that's going to drive what we're doing is investment in a generation facility, so an electricity generation facility. So in that case, if you want to make the investment, of course you will make electricity, produce electricity, and you will get some price for that electricity, and that price P, that's going to be uncertain. So that's where our uncertainty gets into the picture. So let's assume indeed that this price for electricity that we're going to generate in the future is indeed governed by this geometric right-hand motion process as we see here. So that means once this, and we're going to abstract away from costs here, so get to costs at the later stage. So when we have a finished plant, it has some worth, what's going to produce electricity all the time. The electricity priced at price P, which is governed by geometric right-hand motion, and as we have seen, the value of such a finished plant, which produces a constant, or a stochastically growing, actually I should say, output P divided by P will have a value P divided by R minus mu. So this is growing uncertain perpetuity value. So once we make the investment, which has my investment cost I, we get this V of P. Now, until we have made the investment, of course we get nothing, but we do have the option to make the investment, and that option is going to have some value as well. And we do want to figure out at what price, at what P star, at what threshold level should we be willing to actually make this investment. So that's again represented by this picture here. So how long do we have to wait until this blue price here, until what threshold, basically how high does this price have to grow before we want to make this investment I to get basically the value P over R minus mu. So that's a question. So we're going to deal with that question by using this Bellman equation, but now with investment. So again, in discrete time, the Bellman equation was the maximum, this V of P, the value of this option is the maximum of what we could get if we exercise it right away. So this NPV, or the value that we get if we wait one period and then again make this assessment, do we want to invest at that moment or wait longer. So that option tomorrow at the next stage will again have a value equal to V as a function of P, with then the P, the price tomorrow, but now discounted by 1 plus R. So that gave us this Bellman equation with this decision that we have to make each period in time. So in continuous time, we should be able to, at each moment again, and therefore at each P that we observe, which is moving up and down over time, we have to choose whether we would like to make this investment right away. And if we do so, we of course get this, the NPV of this project, which is this P over R minus mu, the present value of those cash flows, minus the investment cost I. Or do we want to wait? And if we want to wait, then we get the discounted value, continuation value. And the question then is, how is this discounted continuation value, how can we find that? Now the point is that for all the time that we're waiting, so as long as we wait, this value will satisfy a Bellman equation, right? Because that's the continuous time equivalent of this Bellman equation that we had before. So this continuation value, this value of the option to invest before we have exercised it, will again satisfy such a Bellman equation. But now without this first P, and because if you remember, this first term here represented the cash flow, the money that we get while waiting. Well, in this case we get no money while we're waiting because we don't have a power plant yet. So the flow part in this equation, which is its first term, where we first had some just P, now it's 0 because we are not getting any price yet because there is no power plant yet. So we have the same Bellman equation, but with this first term reduced to 0. It's not there. So we need to solve this equation. So the question is, what will this solution look like? Well, at some point price will be so high that it's going to be very attractive to make the investment. So if P is high enough, it will be optimal to make the investment, and at that point this V, this value, will change into the value of the finished plant, so into the NPV, P divided by R minus mu minus its investment cost. On the other hand, if the price is really low, we will not make the investment. It will probably not be worth it. Or in other words, the value of waiting will outweigh the value of getting the NPV right away. So in that regime, and P is pretty low, we imagine that V, this value, will satisfy this Bellman equation. So R times V equals 0, no cash flows yet, plus, or at least, and hopefully starting to get familiar terms, mu times P times the derivative of V, plus a half times sigma squared times P squared times the second derivative of V. And the question that we need to address is, well, of course, this is what happens at very high or a very low price, but at some point there will be a switch, right? These two parts have to be somehow connected at some threshold. So the threshold P star is the price at which we'll switch from the waiting regime to investing into this plant. And we need to figure out what price P star, or threshold P star, will be the optimal one. So what this is then going to look like, again, this picture, as long as P is below this threshold, we'll just wait. P is moving up and down according to this geometric grounding motion process. At some point over here, it will hit the threshold, it will cross that threshold, and at that point it will be optimal to make the investment. And what we need to find is, well, where is that threshold? So at what point will it become optimal to make the investment? And what's the value actually of this waiting option while we're just still below this threshold? So that's what we need to do. What does V of P look like? So what's the value of this option while waiting? Well, we do not get any money, but we do get the continuation value each period. And in order to find that, we need to solve this Bellman equation in this waiting regime. So in this regime where P is still below this threshold that we need to determine. So let's look at this waiting regime. So where P is still low, so below the threshold that we need to determine. So again, this Bellman equation is a differential equation, right? It's this equation. It relates the V of P to its derivative, V prime, and its second derivative, V double prime. And the question is, can we solve that? So, might look daunting, but let's be positive about this. So a couple of years ago, when I started this course for the first time, I also had this picture, this slide actually, but with Obama, who said yes we can, but I decided it's about time to actually update that. So now I have this other guy, so now you know where actually Obama got his slogan from. So yes, we can solve this. Well, how can we solve this? Well, let's try something. Let's imagine, or let's conjecture, let's hypothesize that there is a solution here, and then that solution will take the form of a power function. So what power? Well, we don't know yet. Let's just call that P to the power beta. So that's any power function with a power beta. We don't yet know what beta should be, but we're going to figure out what it is. So let's, now can we figure out whether this solves that equation? Well, let's just plug this in and see whether it solves the equation, right? So let's plug in that the value is equal to some power function, and let's see where that gets us with beta, the power that we need to determine. So this again is the differential equation. We need to plug in that V of P, our conjecture, our ansatz, our guess that V of P is a power, P to the power beta. Well, let me do that. Well, it's on the slide here, but let me also do it actually on paper again. So we have the Bellman equation, R times V of P equals 0 plus mu times P times V prime of P, first derivative, plus a half sigma squared times P squared times the second derivative of P. And let's try whether V, P, the function, power function, P to the power some beta, whether that solves this equation. So what's then V prime? P, the first derivative of a power function, of course, is P times beta times P to the power beta minus 1. And taking the derivative from that will give us a second derivative. Well, again, one derivative brings down this beta minus 1. And here power is lowered again by 1. So that's how these derivatives of course work. So let's plug that in then. So we get r times v of p, well that's r times p to the power beta, equals u times p times the derivative, that's the derivative, beta times p to the power beta minus 1, plus I have sigma squared times p squared times the second derivative, which is over here, beta times beta minus 1 times p to the power beta minus 2. Now what you might notice is that here we have p to the power beta, here we have a p times a p to the power beta minus 1, well that's of course also p to the power beta, and here we have a p squared times p to the power beta minus 2. Again, let's add up the exponents here, again makes it p to the power beta, so we have p to the power beta all over the place. So writing that out explicitly, we have left hand side r times p to the beta equals mu beta p to the beta plus I have sigma squared beta times beta minus 1 times p to the power beta. Now does this work? Well, depends, right? Might depend on what p is, right? But we need this to work. We need to solve this equation for any value of p, for the whole function, for all possible values of p. So if this is to hold for any possible value of p, that may only work as long as the coefficients here are actually equal. So this is going to work exactly when r, well, let's put everything to one side, r minus mu beta minus half sigma squared beta times beta minus 1 times p to the beta equals 0. This holds for any possible p only if this expression in the parentheses here is 0. So for what p to the power beta is this equation solved? Well, for any beta for which the stuff in parentheses here is going to be equal to 0. So let's look at that on the slide again. So there we are. So this is precisely that expression. Well, some stuff on the left hand side and some on the right hand side. But we see this p to the power beta on the left and right side. It is only solved for all possible p's as long as these red stuff, the red bits here, are actually equal to each other. So this works as long as beta satisfies that quadratic equation in beta. So this r is a constant, of course, it's a parameter. Mu is a constant or a parameter. Sigma, or sigma squared, is constant, again a parameter. So figure out the beta that solve this equation. Well, for that beta, p to the power beta actually will solve this differential equation for any p. So, well, that's it, right? So can we solve this equation for beta? Well, if you look at this as an equation of beta, it's a quadratic equation. So can we solve a quadratic equation? Well, hopefully we can. So to summarize that, so we had this Bellman equation, and we figured out that it's solved by p to the power beta as long as beta satisfied that quadratic equation. And I told you this quadratic equation, we can solve quadratic equations, but in how many ways can we solve it? So how many solutions does a quadratic equation typically have? Well, think about this a bit, stop the video, and then once you know the answer, you can carry on. And of course, a quadratic equation typically has, well, at most, 2 solutions. And those 2 solutions you can actually compute, right, using the ABC rule. So you know that from your high school experience. So there's 2 solutions typically, well, at most 2 solutions, I should say, to a quadratic equation. Will be expressible in terms of the parameters by using the ABC rule or the quadratic expression. and I'll call them beta 1 and beta 2. And if you work a little bit harder, you can figure out actually that this beta 1 will be a solution which is going to be bigger than 1, and this beta 2 will be a number which is going to be smaller than 0 always, whatever mu, sigma, and r are. So we have actually not one solution, we have two solutions. Both p to the power beta 1 and p to the power beta 2 will work. They will solve this Bellman equation, this differential equation. And in fact we have even more, because any combination of those two, so some a, any a, constant a times p to the power beta 1 plus a b, any b, times p to the power beta 2 will also solve that Bellman equation by virtue of linearity of that equation. So you want to check them actually, check that whether this expression actually solves that equation. So instead of finding one solution, we actually get a large array of solutions, a large set of solutions characterized by any choices basically of this a, this capital A and this capital B. So for any constants a and b, this function will actually solve that Bellman equation. So which one is the right one? That's the next question. So where do we stand so far? So we have v as a function of p. Well, we know that as p is above some value, p star, we will make the investment immediately. So then the v of p will be equal to the NPV. That's the first bit. On the other hand, below this threshold, we will be in the waiting regime, so we will not get any cash flows, but v of p will satisfy the Bellman equation without these cash flows. And we just figure out what its solution is. So in general, it looks like this combination of these two terms, these two power functions. So let's look at that in the picture. So if p is below p star but above 0, we have the waiting option, which has this value, which satisfies the Bellman equation. If p is above this threshold, the value of this project will be the same value that we get if we immediately invest, because that's what we should do at that moment. So we have to figure out, so where is that p star? So what is the value of p star? So what is the optimal threshold when we should invest? And what are those a's, and what is the a parameter and the b parameter here? These constants, what value should they take? So in order to find those optimal values, we need to impose some additional conditions. And the additional conditions that we are going to impose is, first of all, that when price is equal to 0, so when this value of electricity, the price for electricity drops all the way to 0, then it will stay there forever. That's what happens with geometric wave motion. Once it's 0, it remains at 0. So that means that at that point, this option to invest will be worthless, because never again will p grow above p star. So we demand that as p goes to 0, the value of that option should be 0. That's one boundary condition. And then at the other boundary of this waiting regime, threshold p star, we are going to demand that these two solutions, so the left-hand solution over here, the right-hand solution over here, that they are going to match up nicely. So what does that mean, matching up nicely? Here's the right-hand solution, the NPV. Here's the left-hand solution, the blue bit, the option value. And matching nicely means having a smooth fit at this p star. So we want to make sure that this line is actually continuous, but even more so differentiable. Well, let's first look at the condition, the first condition on the left-hand side, when price equals to 0. We want the value of this option to be 0 when price goes to 0. So we know that for prices below this threshold, this was the expression for this option value. It consists of these two power functions, and we want to know what's going to happen when price is going to be equal to 0. Well, let's have a look. Let's just plug in p equals to 0. What happens if p equals 0? Well, this first term, so remember this beta 1 was bigger than 1, so 0 to some positive power, well, that's 0. So indeed, this first term, whatever a is, this first term nicely goes to 0 as it should. Option value is 0 as p goes to 0. The second term, however, is more problematic. So remember, beta 2 was a negative number. So what does that mean? A negative power. So p to the power minus some number, well, that's like 1 divided by p to the converse, right? So x to the power minus 1 is 1 divided by x. X to the power minus 2 is 1 divided by x squared. So here we cannot just plug in p equals 0. It will actually explode, right? So 1 over x is going to explode if you plug in x equals to 0. It's going to infinity. So we can't have those solutions there. So it must be the case that if we want value to go to 0 if p equals 0, that this b constant, we must choose that equal to 0. So that fixes b equals to 0. So a can be anything, that's fully consistent with option value going to 0 if price goes to 0, but b cannot take a non-zero value. B needs to be 0. So that gets us one of these constants, b equals 0. A can still take any value. Now we still have to figure out what a is, and we need to figure out what this threshold p star is. So still two things to be set. And we're going to do that by demanding this smooth fit. So what we need as we get near the point of investment, the value that we have just before investing and the value that we have just after the investment, just around this p star, must first of all be continuous. So continuous as we cross this point p star. So it should not really matter whether you're just below or just above that point. Total value should be the same. So this is called value matching, and it says the value of the option at this particular point p star, so at this threshold, should be exactly equal to the NPV at that point, p star divided by r minus mu minus I. So that's one condition. But we have two things that we need to set. So one equation is not sufficient to figure out both a and p star. So we need one more condition. And this other condition is basically related to this, our choice being the optimal choice, and that's going to be this smoothness, differentiability. So this optimality is going to require that these values are not only continuous, but they are actually matched smoothly at this threshold p star. What that smoothly means that even the derivatives must be the same at that point. So the derivative of our option value, p prime, and this p star, so the derivative of the value while waiting, should be equal to the derivative of the NPV when we make the investment. So if you remember, the NPV was this thing. If you take the derivative with respect to p of that NPV, that's 1 divided by r minus mu, right? So this is the derivative of the NPV. So these derivatives should match up as well. So that's called smooth basting. So we have a smooth basting condition saying that these derivatives should be the same. We have this continuity equation saying that the values themselves should be the same. And now we have two equations and two unknowns, and we can solve those for these two unknowns, a and p star. So let's look at those two equations. So continuity is also called value matching. So the values need to be matched at p star. So a times p star to the power beta 1, which is what we have on the left hand side, should equal to the value on the right hand side, p star divided by r minus mu minus I, the NPV. And the derivative of those things, left hand side, should equal derivative on the right hand side, which is called the smooth basting conditions. So what you need to do is actually solve these two conditions for both a and p star. So these are two equations and two unknowns. Solve those. And let me give you a tip here. What's going to be convenient is to multiply the first equation, the value matching equation, multiply that all over by beta 1. And if you multiply the second equation, left hand and right hand side, by p star, then those left hand sides will become the same. But if that's so, then also the right hand sides will become the same, and that will give you what your p star is. And once you know what p star is, then you can figure out what a should be. So if you do that computation, you'll figure out that this investment threshold, so this p star, is going to be as follows. It's going to be optimal to invest if provided that this threshold p star satisfies the condition that p star divided by r minus mu, so the present value essentially at the threshold, should equal not I, not the investment cost, but I multiplied by this beta 1 power, this positive power, right, bigger than 1, divided by that same beta 1 minus 1. So remember, beta 1 was this power which was determined in terms of the parameters of the process, right, of the mu and of the r and of the sigma. was a solution to this quadratic equation, which is a number bigger than 1. So if beta 1 is bigger than 1, then actually also this whole fraction is going to be bigger than 1. You might want to verify that. So this is actually telling us that this right-hand side is actually bigger than I. So you want to wait until your price reaches the threshold, P star, such that the value, P star over R minus mu of the future cash flows, is actually some number slightly bigger than I itself. If you compare this to the classical NPV criterion, it says you have to wait until the value is equal to the investment cost, right? When the NPV gets positive. Here it has to be strictly bigger than the investment cost, and the reason is there's also option value here that you are throwing away when you are making the investment. So this is an opportunity cost. Exercising your option and not having it anymore is an opportunity cost in addition to the investment cost that you have to take into account when making this decision to do this investment. So here's a picture again. So on the right hand side, so here's P again, so here's this threshold P star, so here's P bigger than P star. So here actually the value of this option is just the NPV. So this dashed line, P divided by R minus mu minus I. That's the dashed red line. On the left hand side, this NPV goes nicely to 0. So the traditional NPV analysis would say, well, as long as P is above this point, you should invest, because then we have a positive NPV project. Well, in this real option context, we're actually saying, well, there's actually some additional value. This value from waiting, and that's this blue line, the V of P that we saw. So the A to the power P, A times P to the power beta 1. That's this blue line. And you see that nicely matches in a smooth fit here to this NPV. But here the option value is actually higher than the value of making the investment right away. So here we should wait with making the actual investment decision. So the interpretation is indeed that. So optimal investing means wait longer than the NPV rule. So you don't want to invest as soon as the present value exceeds the cost, but you have to take into account this option value. This option value says, well, the value of keeping the option is actually more than what you get than if you exercise this thing right away. And if you invest, you give up this option value. So that means that this is an additional cost, an opportunity cost in this case, to investing. So how large is that value? Well, that depends on this process, right? So what happens in particular is that the larger the volatility, so the larger the uncertainty, the larger also the option value. So you know this as a sort of rule of thumb from option pricing as well. Larger volatilities means larger option values. Well, same holds here. So the longer you wait, so the larger the volatility, the longer you wait. So this P star actually, this threshold is going to be higher as sigma is getting higher. Why? Well, this beta 1 also depends on sigma. And you'll figure out that as sigma increases, this coefficient here is actually going to increase. So it's going to increase P star. So what that looks like in a picture is like this. So this was what we had for a given sigma. If we take a slightly larger sigma, the beta is going to be different. So this value V of P is going to be slightly different. It's going to be this black line for a higher sigma. So still it matches smoothly to this red line of NPV, but at a higher point. So with a higher volatility, we'll have a higher threshold, P with 2 stars, at which again the option value, the black line now, actually matches this this NPV, and you see that the option value is now always higher than the option value that we had with the lower sigma. So the higher sigma yields a higher option value V of P, represented by the black line. So let's wrap up then to come to a conclusion. So we figured out what the Bellman equation was in continuous time. So it took the form of this differential equation. So I had a first look at that. So we figured out this in this weighting regime, we could actually solve this equation by, in general, this particular form. So the sum of two different power functions, one positive power and a negative power. Well, which are the correct ones? Well, we had to figure that out by imposing these boundary conditions, both at p equals 0, but also at matching up this weighting solution to the investment solution. So that was this value matching and smooth pasting conditions. So we're going to expand on that next week, looking at a paper actually, which does this in a slightly more complicated model, paper by Morton A. So we're going to look at that in a lot of detail next week. To prepare yourself for that, there's an assignment. So the assignment will actually be due next week, Wednesday, just before the lecture on Wednesday, when I will discuss actually this assignment. So you can hand it in afterwards, of course. So you have to hand it in on Nestor through the link, the upload link. Before that time, you can actually do the assignment in a group or individually, what you wish. Maximum 3 persons, and make sure that I know who's in your group. It could be a different group or the same group, what you wish that you used before. And what I'm going to ask you basically is do this analysis for a slight variation basically of the model that we looked at here. So I'm going to ask you to solve an investment model which is not the revenues or the price or the profits which are stochastic, but the costs, C, are stochastic, and the value that you get when you invest is B, is going to be given. And then the question is, how low should the cost go before you make the investment? So instead of the investment cost I, we'll have a stochastic investment cost, which we call C. And as that declines, at some point you will make the investment. And I'm also going to ask you to graph actually this threshold a cost level as a function of the volatility sigma. So for doing that, you'll need to use some program like Excel or perhaps some other program that you like to use. So that's it. So I hope to see you next week again. I hope to see your assignments as well, and have fun solving that. Bye bye.